Have you ever wondered how AI models, especially these huge ones looking at tons of, well, unlabeled data, just seem to get things? It feels a bit like magic sometimes.
It really does. It's one of the biggest questions in machine learning right now.
Exactly. But today we're going to dive deep into a really fascinating theory from Ilya Sutskever, who's, a major researcher in AI. He has this simple but honestly pretty profound idea about why the most powerful AI systems actually work. And it comes down to compression, learning by compressing data.
It's a really elegant way to frame it.
So our mission for this deep dive is to really unpack why unsupervised learning, which is, let's face it, the engine behind so much of today's AI, works so well. We want to explore Sutskever's idea about compression and how it might just give us some solid answers. Hopefully this helps you get a better handle on the fundamental principles behind these systems.
Yeah, moving beyond just seeing that it works to understanding a bit of the why.
To get us there, we've looked through a study guide, a detailed briefing, and the full transcript of Sutskever's talk, an observation on generalization. We've tried to pull out the key bits.
It's a great talk, definitely worth digging into.
Okay, let's start with the basics. The tale of two learnings, right? Supervised versus unsupervised.
Right.
So supervised learning, that's the one we generally feel we understand better. It's the bedrock, maybe.
Yeah, you could say that. It's where you have labeled data.
Exactly, like showing a model pictures and saying, cat,
Yeah.
dog, cat. Sutskever points out there's a, quote, precise mathematical condition under which learning must succeed.
Mm-hmm.
It's like a clear recipe. If your model makes few mistakes on the training data, isn't overly complex compared to how much data you have, and the test data looks like the training data, well, math says it's guaranteed to work well on new stuff.
He even calls it conceptually trivial,
Yeah.
which is quite a statement.
It is, but his point, I think, is that the core guarantee is mathematically straightforward.
Right, it comes from established theory. Yeah. Things like pack learning, statistical learning theory. He even, sort of cheekily perhaps, says 3 lines of math can prove all of supervised learning.
Wow.
Now, he does acknowledge things like VC dimension were discussed a lot historically, but he argues that was mostly about handling sort of theoretical issues, like infinite precision numbers, which, computers don't actually use. With finite computer floats, the core ideas are simpler, he suggests.
Okay, so supervised learning. Clear path, mathematical guarantees, conceptually, maybe even trivial if you squint right.
More or less, yeah. But the foundations are solid.
But then, unsupervised learning. This is where the mystery comes in, as he called it. This is where models look at huge piles of data with no labels, just raw text, raw images, and they're trying to find something.
Yeah.
Hidden structures, patterns.
That was the old dream, wasn't it? That AI could just look at the world, essentially, without explicit instructions and somehow figure out the underlying reality.
And that dream, I mean, we look at models like GPT-4, it feels like it's been fulfilled empirically, right? These things are incredibly capable.
Absolutely. The empirical results are stunning. But the why? That's still fuzzy.
Yeah, and Sutskever nails the confusion. He says, you optimize one objective, but you care about a different objective, and yet it helps. How can that be? Magic.
Yeah. It's a great quote because it captures the feeling perfectly. You train a model to, say, predict the next word in a sentence really well, and suddenly it's great at summarizing articles or answering questions, tasks you didn't explicitly train it for. The connection isn't obvious.
Like learning to juggle makes you better at swimming. It feels disconnected.
Exactly. Or maybe optimizing for reconstruction error, just trying to recreate the input, somehow leads to better performance on a classification task later. From a theory standpoint, it feels, inaccessible. How does optimizing this help that?
So that's the puzzle Sutskever wants to solve. Now, before jumping into his main compression idea, he does mention one specific type of unsupervised learning that does have a guarantee.
Right. Distribution matching. He says it's not widely known.
Yeah. Can you walk us through that quickly?
Sure. So imagine you have 2 piles of data, X and Y. Maybe X is English sentences, Y is French sentences. Crucially, there's no direct link, no sentence-by-sentence translation provided.
Okay, just a bag of English, a bag of French.
Exactly. Distribution matching tries to find a function, let's call it f, that you can apply to x, so fx, such that the distribution of fx looks really similar to the distribution of y.
So make the transformed English feel statistically like French.
Pretty much. And if the data is high-dimensional enough, like sentences are, this constraint making the distributions match can actually be enough to pin down what f has to be. It almost forces the discovery of the underlying relationship.
Interesting. So there is a corner of unsupervised learning with guarantees.
Yes, but he notes it's maybe a bit artificial compared to how we usually do unsupervised learning. Still, it shows it's possible to have theoretical assurance. It's like finding one solid bridge across the mysterious river.
Okay, so that's one bridge. But Sutskever's bigger idea, the main bridge maybe, is this concept of compression.
Yeah, this is the core of his argument.
He makes this really bold claim. Compression is prediction, and prediction is compression. They're two sides of the same coin.
A one-to-one correspondence, he says.
But he argues that thinking about it in terms of compression gives us a better handle, a better intuition for why unsupervised learning works.
It really reframes the problem. And his thought experiment here is key. You really have to picture this.
Okay, lay it on us.
Right. Take two data sets again, X and Y. Let's say X is, I don't know, a massive amount of text from the internet, unlabeled.
Okay.
And Y is your specific, maybe smaller labeled data set for a task you care about, like classifying emails as spam or not spam.
Got it. Unlabeled ocean, labeled island.
Nice analogy. Now just stick them together. Concatenate them into one giant file, X followed by Y.
Okay, just smush them together.
Just mush them together and feed this giant file into a really, really good data compressor, a sufficiently good compressor, as he puts it.
Like WinZip on steroids.
Exactly. An idealized ultimate compressor.
Yeah.
Now, what will this compressor do? It's going to find patterns everywhere to save space. Crucially, he says, it will use the patterns that exist inside X, the unlabeled text, to help it compress Y, the labeled emails, and vice versa.
Ah, so patterns in the general text help it compress the specific email data more efficiently.
Precisely. And the amount of extra compression you got, because you put them together, the additional compression gained by concatenation, that saving in file size is a measure of the shared structure between X and Y.
Wow.
He calls it a kind of algorithmic mutual information. It gives you a concrete mathematical reason why having that big pile of unlabeled data, X, actually helps you with your specific task, Y. It generalizes that distribution matching idea, too.
That actually makes a lot of intuitive sense. The better the compressor, the more it finds those shared patterns, the more the unlabeled data helps.
Exactly. It connects the two seemingly separate worlds.
Okay, so if compression is the framework, what's the goal then? He talks about achieving low regret. What does that actually mean for someone, say, training one of these models?
Right. Low regret. It basically means your learning algorithm has squeezed out all the possible help it could get from that unlabeled data.
All of it.
All of it. It's done the best job at benefiting from my unlabeled data. You've reached a point where no one could have done as good of a job as me in terms of leveraging that unlabeled information for prediction.
So it's like you can be confident you haven't left any useful predictive patterns from the unlabeled data untapped.
Exactly. Whether that unlabeled data ultimately contained super useful patterns or not, you know you've extracted everything possible from it. You've minimized your regret about potentially missing something useful in X that could have helped with Y.
Okay, that's a clear goal. Maximize the help from unlabeled data via compression. Now, how does this connect to the theoretical limit? He brings in Kolmogorov complexity.
Ah, yes, the ultimate theoretical benchmark. Kolmogorov complexity, KD, of some data D, is defined as the length of the shortest possible computer program that can generate D and then halt.
The shortest program. Like the most compressed representation imaginable.
Essentially, yes. It's the ultimate compressor in a theoretical sense. Now, the catch is you can't actually compute it for any given data set. It's theoretically impossible to find that shortest program in general.
Right. It's not like you can just run find shortest program my data.
Unfortunately not. But it serves as a vital theoretical concept. And specifically, he talks about conditional Kolmogorov complexity, KYX.
Okay, what's that?
That's the length of the shortest program that outputs Y if it's given X as an input. So how much shorter can the program for Y be if it already has access to X?
That sounds definitionally like what unsupervised learning is trying to do. Use X to help understand or predict Y.
Bingo. He says KYX is definitionally the solution to unsupervised learning. It perfectly captures the idea of extracting all predictive information from X about Y.
But wait, if we can't compute it, and also, how does this relate back to just compressing the concatenated file?
Great questions. First, the uncomputability means it's a theoretical target, not a practical algorithm. Second, interestingly, Sutskever points out that for maximizing predictive value, just compressing the concatenation, X followed by Y, with an ultimate compressor is basically just as good as using a specific conditional compressor, KYX.
Really? Why is that?
Because a good enough general compressor, when compressing X and Y together, will implicitly have to figure out the conditional relationship KYX anyway to get the best overall compression. So you don't need a special conditional machine, just a fantastically good general one.
Okay, so the theoretical ideal is this ultimate uncomputable Kolmogorov compressor. How on earth do we get from that to giant neural networks actually working in practice?
Yeah, that's the million-dollar question, right? And here, Sutskever makes another really interesting analogy. He suggests that training large neural networks using stochastic gradient descent, SGD.
SGD, the workhorse algorithm for training most deep learning models.
Right. He says doing that is automatically like doing program search over a computer. He views neural networks as little computers themselves.
Little computers, how so?
Well, they take inputs, perform a series of computations through their layers, their circuits, if you will, and produce outputs. And SGD, the training process, is the mechanism that finds those circuits from data. It's searching through the space of possible programs the network can implement.
Huh. So training a neural net is like automatically searching for a compact program that explains the data.
That's the analogy he draws, and it leads to a key insight as these neural networks get bigger and bigger.
Like GPT-3, GPT-4, massive scale.
They become better and better approximations of that theoretical Kolmogorov compressor. They have more capacity to simulate complex programs to find intricate patterns.
So bigger nets, closer to ultimate compression, less regret, better use of unlabeled data.
That's the argument. Less and less regret as we train larger and larger neural nets. And things like architectural innovations, he mentions the transformer replacing RNNs are seen as ways to build better miniature Kolmogorov compressors. They overcome bottlenecks that limited older architectures.
It makes the drive towards scale seem less like brute force and more like trying to build better approximations of this theoretical ideal.
Exactly. But it is still an analogy. He's careful to point out that SGD is a weak search procedure. Unlike an ideal search, the order you see the data in matters, other training dynamics matter. It's not perfect, but it's surprisingly effective.
Okay, so the theory is unsupervised learning works because large neural nets trained with SGD act like approximate compressors, finding shared structure, which is equivalent to prediction, approaching the theoretical limit of Kolmogorov complexity.
That's a pretty good summary, yeah.
Does he offer any direct empirical proof beyond just, large language models working well?
He does. He points specifically to an OpenAI experiment from 2020 called iGPT.
iGPT, what did that do?
They took images, but instead of treating them as 2D grids, they flattened them into long sequences of pixels, like reading a book, but the book is just pixel values.
Okay, turning images into text, basically.
Sort of, yeah. And then they trained a transformer model like the ones used for text to do next pixel prediction. Given a sequence of pixels, predict the color of the very next one.
Which, according to the theory, is equivalent to compressing the image data, right?
Yeah.
Maximizing the likelihood of the pixel sequence is compression.
Exactly. And what they found was really compelling. They tested this on standard image datasets like CIFAR-10.
Right.
And they saw a clear pattern. The larger the iGPT model, the better it got at predicting the next pixel, meaning better compression, lower loss. And also, the better its features were for a downstream task. They measured this using something called linear probe accuracy. Basically, how well can a simple linear classifier distinguish between classes, like cat versus dog, using only the features learned by the unsupervised iGPT model?
And the better the compression,
the better the linear probe accuracy. It showed a direct link. Improving the unsupervised compression objective led to learning more useful representations for supervised tasks, even for images.
That's pretty strong evidence connecting compression and useful feature learning.
It really is. It took the theory out of just the realm of text and showed it holds up in vision too.
Okay, so the theory seems powerful, connects a lot of dots, has empirical backing. But does it explain everything? Are there still mysteries?
Oh, definitely. And Sutskever himself points them out. One big one is, why do linear representations emerge so often?
What do you mean by linear representations?
It means the features learned by the unsupervised model are useful even when you just plug them into a simple linear classifier for your downstream task. The iGPT result is an example of this. It happens all the time, he says, but the compression theory doesn't explicitly predict why the learned features should be linearly separable.
So the theory explains that useful features are learned, but not necessarily why they have this nice linear structure.
Sort of, yeah. It's a nuance the core theory doesn't fully address yet. He does speculate a bit.
Oh, what does he think?
He wonders if maybe autoregressive models, like iGPT predicting the next pixel or token, might naturally produce better linear representations than, say, BERT-style models that predict masked-out words.
Why would that be?
His hypothesis is that predicting the next thing forces the model to capture longer-range dependencies in global structure, whereas filling in a blank, masked prediction, can sometimes be done using just local context. Maybe that focus on global structure leads to more linearly useful features. It's just speculation, though.
Interesting. What else?
Well, another big one is compute cost. The theory, especially the Kolmogorov complexity part, is mostly about information. How much can be compressed, how much structure is shared. It largely ignores compute cost.
But compute is huge in practice.
Yeah.
Training these models costs millions.
Exactly. So while the theory explains information theoretically what's going on, it doesn't fully grapple with the practical constraints of computation time and resources.
Right. And he mentioned diffusion models, too, the ones that generate images.
Yeah, their behavior adds another layer of complexity. Some diffusion models are incredibly good at generating realistic images, but they don't necessarily achieve the absolute best likelihood scores. They aren't necessarily the best compressors in a strict sense. So how do they fit into this picture perfectly? It's still an area of active research and maybe some mystery.
Okay, so lots explained, but still some fascinating open questions.
Always the way in science, isn't it?
So let's try to wrap this up. We started with the puzzle of unsupervised learning, how AI learns without labels. Supervised learning, pretty clear path. Unsupervised. Felt like magic.
Right, the empirical success was way ahead of the theory.
But Ilya Sutskever's theory gives us a powerful lens. Compression. Large neural networks, trained with SGD, are acting like miniature Kolmogorov compressors.
They're finding shared structures in data by trying to represent it as compactly as possible. And this process of compression is prediction.
Which means they get better at leveraging unlabeled data, reducing their regret, and ultimately powering the incredible AI capabilities we see.
It provides a unifying framework.
So for you, the listener, hopefully this deep dive helps you see beyond just AI works to glimpse a fundamental why.
Yeah, understanding how things like data compression, predicting the next word, finding useful features, how they're all deeply connected through this idea. It's about efficiently encoding the structure of the world.
So here's a final thought to leave you with. If our best AI models are, in essence, really, really good compressors approximating a theoretical ideal, what does that imply about intelligence itself? Is intelligence fundamentally about compression and prediction?
That's a deep one. And if the theory still has gaps, like fully explaining linear features or factoring in compute cost, what other principles might be out there, what discoveries could unlock even more powerful or maybe more efficient AI down the road?
Lots to think about. It really reframes how we might view the progress in AI.
Absolutely. It's less magic, more math and compression, perhaps.